Good morning, good afternoon, good time, everyone. I'm Mohsen Miri, Director of Strategic Partnership at Phase One, and together with Itai Ben Schechter from Skyline, we are going to talk about pixels to perception, what the journey would be inside Skyline's PhotoMesh automation and also globe dissemination. Hi, Itai, great to have you. Can you
Thank you.
just introduce yourself and talking more about yourself?
Thank you. Just a second. Thank you for having us. Look forward to discussing all the great data we've been reviewing from the phase one sensors and cameras. And look forward to a great webinar.
Great. Thank you, Itai. To start the webinar, I would like some contribution from your side to know about your business, what's your focus today, what's your needed GST and also resolution. So we start with a poll, and it would be great if you answer this question related to your business. So the poll is started. So I hope you can see the poll and your answer in the poll. Perfect. Just some more seconds. Thank you very much. So we go back to the presentation, just starting to share the slides. Just trying to find the poll. Sorry about that. Okay. Maybe Annika, if you're seeing the poll, can you stop the polls? Then I can continue. Great. So what is pixels to perception? Pixel to perception is a journey from images towards the AI, artificial intelligence, geoanalysis, and image analysis. So this is a collaboration between phase one and partners and customers to help you simplify your workflow, streamline workflow, and also end-to-end solutions to your environment. It helps you bringing your business to the next level and somehow saving you from dead ends workflows with a variety of software on the way and simplifying the workflow and streamlining the workflow for your production and your performance from confusions to simplification in integration of data and also products to have the analysis at the end. So it is always the message of Pixel to Perception, call for collaboration. Let's get it together with our partners, software partners and hardware partners to make your life easier. The journey in this session is pixel process and perception journey. So that means we have from the phase one side the cameras and solutions. We will have on Skyline side the workflow and products. And also at the end, we will have the data processing and analysis based on the data that we are producing. The business of phase one is pixels. We take care of the images and every single pixel matters to us because we take care of the imagery resolution, calibration, and all the information you can capture from the images. Phase one at a glance is a more than 30 years company in imagery market. The headquarters is in Copenhagen, and we have offices in Denver and also offices in Asia. Our cameras are produced in Japan, and we have more than 40% R&D and development colleagues. And we are producing cameras for both heritage and photography and also geospatial. You're seeing more than 4,000 of our cameras are in the last couple of years just observing the Earth and doing the Earth observation from sub-millimeter towards the countrywide mapping resolutions. Phase one's core industry is based on the core cameras and also components. We name them. That means the body cameras and also the lenses, as well as the controllers to provide you and also our integrators, our OEM and hardware integrators to combine and integrate these solutions with hybrid sensors like LiDAR, like thermal mapping, etc. And obviously, we have integration kits, which is image SDK and camera SDK, to make this communication between hardware, that means our camera, and the other hardwares like LiDAR, and also towards the workflow. So we produce the sensors and also lenses ourselves. On the systems we make based on our camera components and lenses, our systems. We have compact system and full size system. PAS 150, PAS 280 are compact systems for smaller aircraft, for smaller businesses. Somehow, if you would like to start coming to this geospatial business, it's a very, very good start with that, and has the focus of corridor mapping, forestry, etc. And we have full size systems with PAS 880 and PAS PANA for city modeling and countrywide mapping. So if you are seeing here PAS, abbreviation of PAS, which is phase one aerial solutions. As I mentioned, PAS 150 and PAS 280 are really suitable for smaller aircraft if you would like to fly for corridor mapping, for forestry. With PAS 150, you have the flexibility of choosing lenses, different lenses, and with 280, you have larger swath for these type of projects. You're seeing in this image PAS 880 and PAS PANA, which are for larger and bigger aircrafts. Here you're seeing an aircraft from Eagle Forestry Geotechnologies. You will see some of the data set we captured with Eagle Forestry over the Little Rock area in Arkansas, and doing smart city projects, and also using PANA. PAS PANA is suitable for countrywide mapping. We have also cameras for drones. With P3, if you install 100 megapixel, or if you're interested in global shutter cameras, GS 120, you can go to sub-millimeter accuracy with P3 payloads and using in copter drones, as well as using P5 for fixed wing drones, which is sub-centimeter and survey grade mapping in many applications. How do we ensure the journey of light? So it is always the matter of how we get the light, how it goes through our lenses and shutters, and also at the end to the body or the sensor, how we manage it, how we can keep this fidelity of colors from the nature toward the sensor and make it digitized. We take care of accuracy in camera calibration. Our camera calibration or system calibration includes sensor calibration, lenses, synchronized shutters in our systems, shutter speed, which manages really the sharpness of our images, and you don't really need to have any motion compensation in your system, which are too expensive. And we manage all of these configuration with our cameras, with navigation sensors, GPS, and IMU, as well as the other hybrid sensors inside in our calibration. We take care of the images in the way that we take care of quality and color fidelity. We take care of illumination, brightness, exposure, contrast, and sharpness to be always delivered as it is. So it is the topic of reality capturing, and it is for us somehow I believe that we capture the reality as close as possible. The journey of light is very challenging in aerial surveying. You have always an uncontrollable light solution. So we have just the sun, and the sun goes toward the atmosphere. We will have the haze, we need dehazing, we have shadows, we have darkness, we have different colors, etc. And we need to enhance these images. That means we need to use all the capabilities inside the images. Here are some examples from the dataset that AI will show the end results and in the following parts of this session. This is an IIQ image, which is a raw format of phase one cameras. This is a non-processed data you are seeing, an image. And in the next image, I would like to show you how the shadow, texture, and sharpness will be managed because we have all this information in phase one's raw format. In this image, you see we can go towards the image in the shadowed area and also in the very low texture area. In a more exaggerated way, or let's say zoomed in, you see here in the shadowed area of the large building you are seeing in the dataset. It's the PAS 880 dataset in the area of Little Rock. I would like that you observe the shadowed areas in window and also on the streets. If you see some cars or all cars, and also in the vegetation areas, and see what happens in the next image. You see everything comes out of the shadows because we have the full capacity using the high dynamic range of the phase one images. On top of the building, you see the texture of the roof is extracted somehow, and it is not overexposed. And on the bottom of the building, you see the color fidelity on the flowers, let's say the pink area, and also the white flowers on the right side areas, and also the black car, which was somehow hidden in the shadow area, is now extracted. This image is an IIQ again, and in next image you see how the white area, which is somehow overexposed, shows the textures. You see all behaviors of the roof, which is a very sunny day, captured in a very sunny and high illumination. Everything comes out of the overexposed area. This is my favorite one, which is somehow the ventilator. And in the next image, you see the sharpness in overexposed, or let's say in the high exposed area, and also in the underexposed area, how everything comes out of this. So this is again the PAS 880 data set. We are flying over more than 2,900 meters, and we can extract really even sub-centimeter resolution on top of the buildings. Just coming back to see where this part of the image is and how we can capture this information. Another file or another image is from P5, which is very fantastic. I like also this image because it shows in the dark area, you see here between the bright and dark area, how much is the difference between the values. And in the next image, you extract everything in the dark area, and the difference and the balance between the range of the bits can be adjusted. With the P3, it is even more important because you have this instrument I call phase one cameras measurement instrument. You want to have this instrument to measure cracks. You want to have this sub-millimeter accuracies to run AI-based crack detection. And in shadowed areas and low texture areas, it's very important to extract these, let's say, objects out of the challenging illuminations. Why IIQ? IIQ is intelligent image quality. It is the raw format of phase one. Somehow we talked always about the performance data streaming because IIQ is much smaller than any other format outside the lossless compressed formats, and it is even smaller than its JPEG image. Uh, and if you convert it to TIFF, 8-bit or 16-bit, it would be 5 to even sometimes 7 to 8 times larger. Imagine if you fly an area or over a city and you want to have more, much more, 5 times, 7 times more data. But it is not the importance that we would like to talk about IIQ. Is about the images and the capability that I showed in the previous images. And it is a data format that has the dynamic ranges and also the quality of images, and it is easily over the image SDK integratable into the software workflows. So the second poll starts, which is what's your biggest challenges in photogrammetry workflows with your existing software? And after that, so I'll start the poll now. Perfect. I will give you maybe 30 seconds to 40 seconds. After this poll, we will talk about what is the workflow in data delivery, data preparation inside phase one. And after this, we will hand it over to Itai and leave the rest of the webinar in Skyline environment. All right, I give you 5 minutes. 5 seconds, sorry. Great, thank you. So we stop the poll now. If Annika helps me to stop the poll. Thank you. So inside phase one, we have a workflow which starts from planning, it goes to operation, and then goes to processing. So we name this package, software packages or software suite, IX Suite. IX Suite contains IX Plan for planning your flights, IX Flight Pro for doing your operation during the flight and data capturing, image capturing, and also doing the QC. It's very important to do it in the air before you land. And if there is something you should recover, you should refly, you can manage it before you land because it's very expensive. You land and re-plan the flight. And after that, it goes to IX Process, which is a software to convert the images from IIQ or manage the color balancing, etc. And also generating formats like TIFF and so on. So this is somehow a classical way that you can use in Skyline, probably if you like, use TIFF images or IIQ. But there is another option, which is somehow the uniqueness of Skyline here in this webinar, which is the image SDK. Image SDK is the software, let's say, workflow, which is integrated inside Skyline workflow. That means Skyline can consume IIQ images directly without any conversion, without any somehow adjustment, etc. And they can handle it directly, utilizing all the capabilities of images in phase one and go into the next. So you have two options. Either it is integrated in Skyline, or you can convert and do color balancing IX process and then go into Skyline. In IX process, it looks like in this way. If you have, for example, images stitching required, you can do a left image and right image and stitch it together and going with larger swath, or you can utilize the image SDK inside IIQ. You can manage, handle all images individually and having that inside the process inside Skyline and PhotoMesh. So with that, I hand it over to Itai and hope you enjoy the rest of this webinar in Skyline.
Thank you. Here we go. Okay, so we'll give a quick overview of Skyline and the company's history, and then we can jump into the great phase one data and how it processes through the Skyline software. Skyline has been around over 25 years, since the late 90s, with focus on 3D geospatial. We have a very large global footprint in the United States, Europe, Australia, and a lot of different countries, groups of resellers. Okay, on the Skyline vision, we believe in pushing 3D content, creating 3D content, streaming, hosting, making it accessible, and making it scalable. 3D has started out as a very heavy product, a very cumbersome to transfer or disseminate. And Skyline's focus has been using the internet, streaming, and using large-scale computer architecture, parallel processing in order to make 3D more accessible. Out of the key achievements from Skyline in the recent years is really moving from a 2D to a 3D paradigm, thinking of things in the process of creating above ground data and not just 2D orthos. Also scaling up into different views such as holographic displays and utilizing cloud architecture for processing millions of gigapixels. Mohsen was referring to pixels. We look at it as gigapixels, a combination of many images. The dissemination side, we'll go over a little bit how it works on the web. So Terra Explorer is Skyline's platform, flagship platform for viewing, analyzing, performing all kinds of measurements, and it's enabled with a web browser. So we will go over how the different phase one data gets processed into products and disseminated with the Fusion. Skyline PhotoMesh, that is the 3D reconstruction tool. The 3D processing is really unique in the sense that phase one is a large sensor, 120, 150 megapixels, and it could be a combination of cameras, multiple cameras on a single platform, and it accumulates a large amount of data. So Skyline's PhotoMesh is focused on scalable architecture, supporting a lot of different input options and output options. And this is where we get into supporting the IIQ natively. Okay, so on the PhotoMesh inputs, we support really any platform, any camera, any frame base, from a handheld cell phone all the way to very large frame aerial cameras, 300 megapixels, so really anything. On the format side, the typical formats, JPEG, TIFF, other imagery files, but we also support IIQ, like Mohsen mentioned, with the SDK, the phase one image SDK, and that allows us, you can see, to import the IIQs natively with the geo header that they record during the flight. So as soon as the flight is complete, the IIQs could be processed directly in the software. Now this is the IIQ integration. So PhotoMesh supports creating your own IIQ configuration file. We support and different options for creating your own recipe. We provide you with our recommendation for the optimized setting that we consider our best, but you could always create your own. And you can see on the right, the focus in this case is a lot on highlight recovery and shadow recovery, performing some sharpening, being able to add a little saturation or contrast, sort of create a good looking image for the rest of the process, with the focus on maximum details in the shadow and the highlights, utilizing the full bit depth of the IIQ data. Now, one of the things that PhotoMesh enables, once you establish a good workflow for data processing, is a full automation, which could be utilized either on the cloud or locally with a full API that allows you to then queue up projects automatically, process them, have a whole dissemination pipeline for output formats, or push it into a Skyline Globe server or a different server for streaming. And this is really where, if you're doing repetitive work and not one-off projects, this becomes very useful in terms of being able to collect data in multiple sites, locations, all over the world, and have it processed through a central automation workflow. We also allow for local customization. If this is an example of a simplified workflow called the PhotoMesh Wizard, it allows you to just drag and drop images and press build for less sophisticated users. And this could also be customized for specific application, like cell tower inspection, railroad inspection, or let's say transportation mapping pipelines. So this could be a specific workflow for a specific application that could be used by hundreds of users without needing to know the settings in the software. Now, before we jump into the processing numbers, one of the things that I wanted to explain is the PhotoMesh Fuser. The PhotoMesh Fuser is essentially a processing engine that is consisted of 32, about up to 32 gigabytes of RAM and an onboard video card or GPU. And it needs access to the project and where the data through a central server. And that's how you can scale to dozens or hundreds of users and allocate different tasks or steps to a very large process. Okay, so we'll jump into the phase one and PhotoMesh projects. We'll review 4 different projects, starting with the highest altitude and lowest resolution, working the way to the highest resolution. The first one is the phase one PANA. And it's a 2D collect for ortho purposes with an aircraft at 5 centimeter GSD, extremely large scale. The second project we'll review is a 3D focused project from the PAS 880 with nadir and obliques at about 1.5 centimeter GSD. So also pretty high resolution, but allows to scale up to sort of citywide mapping. The first one would be more county-wide mapping. The P5, the Denver sample, that's also a 2D collect. Mosen was mentioned for fixed wing drones, more of a nadir looking vertical camera. And the P3, which is on the gimbal, a stabilized camera for inspection in super high resolution 3D. And this was collected at 0.3 millimeters GSD, so 300 microns. Okay, first one, we'll go over the PANA. So that was about 5 centimeter GSD per pixel, 385 square kilometers. Project was just under 18,000 total images. The PANA, just to give a little bit of a background, is composed of 7 cameras, essentially in a row, with a nadir, a right 1, right 2, left 1, left 2, and then 2 near IRs. The IIQs were imported natively. And the bore sight angles for the different cameras were applied inside the software. The project was 2,700 gigapixels and was processed on 50 PhotoMesh fusers. The IIQ conversion took 4.5 hours. The arrow triangulation, this is the matching, tie point matching, You can see over here all the connections and the tie points. The reconstruction, that's essentially the 2D or 3D process and the ortho writing. And the total project ran in 12 hours, so half a day. What we're seeing here, the total fuser time, that's the total computation time, which was just over 20 days of computation, but allocated amongst 50 fusers. So this is essentially what it would take to process the project on a single laptop. And by scaling to multiple fusers, can be done in half a day. The AT results, really good, just over a quarter of a pixel. A total of 22 control points were used for accuracy verification, and it came out just over half a pixel in the horizontal and just over a pixel in the vertical, so very good results. We'll jump into the project to see what it looks like inside PhotoMesh. So this is the project area. These are the control point distribution. And you can see over here the flight lines. And the images are colorized based on the different collections. So we could see how they import into the software. The collections have the nadir, left one, left two, right one, right two. And you can see in the software, we can apply over here the bore sight correction, roll offset, -27, -13.5. So we could apply all these corrections as well as the camera model and the band definition. Okay, so that's the input into the software. The AT, we'll look at the report. Here are the 22 control points and their general accuracy. You can see over here the GSD map and the distance map, how the images shifted from their original GPS position during the adjustment, and all the tie points. So when we're talking about the parallel processing, when the error triangulation is complete, it splits the project up into tiles, and each tile can run on a separate fuser. So essentially 50 fusers can run through 256 tiles in 5 cycles. Now, if we look at the individual process, each tile produces, for the 2D process, a simplified model. It's a terrain. So it removes any buildings, trees, tries to get a bare earth, and then it creates the orthorectified true ortho model. There we go. Or the 2D ortho, excuse me. Okay, and that's on a tile by tile basis, so we're looking at 2 tiles here. And at the end of the process, we have the full ortho. Also, we build in overviews or pyramids for easy dissemination display. And you can see we're talking about some of the focus on the shadows. The ability to correlate data in the shadows is critical, and working directly on the IIQs, maximum information, clarity, sharpness on the ortho and scale. So this was processed in 12 hours. Okay, we'll jump into the next project. Here we go. Okay. So the PASS 880, that's the 3D oriented camera. It has nadir, 2 nadirs, as Mohsen was mentioning, nadir left and nadir right, and then 4 obliques, forward, back, left, right. This project specifically was 1.5 centimeters, 5.6 square kilometers, and just over 11,000 total images, just under 2,000 images per camera from 6 cameras. 1,700 gigapixels, and this was processed on 100 PhotoMesh fusers. the IIQ conversion, data prep gets through it extremely fast, extremely efficient on 100 computers. The error triangulation was a little bit more intensive, having to calculate 6 different cameras with oblique views, connecting the oblique angles in the nadir. The reconstruction time is really, you see, the most intensive time, and that's 27.5 hours on 100 fusers. So just over a day. And the total processing fuser time was 121 days. So these projects get pretty intensive for 3D, full 3D processing. And that's where the fuser architecture becomes critical to scale it up to just under 2 days, 44 hours. Okay. The triangulation AT results under half a pixel, and you can see the calculated camera model results. So we do perform in situ calibration based on type point observations or control points in order to get the best possible correlation for the 3D process. And we will look at here. This is the Terra Explorer Fusion. So we're opening the project up on the web-based platform. Oh, just a second. It is. And we will, oh, just a second. And open here. Okay. And we also have the project here. There we go. There's the web browser. Okay. So we can see here the layers. We have both the 3D and the true ortho. And the nice thing with the Fusion, other than just a 3D display, we could add information such as parcel maps or addresses. And it's fully interactive, so it has a tooltip, hover. You can click on a building and get the full attribution for it. This also applies to working on the true ortho display. So you can see this is the true ortho versus the 3D. We can see the true ortho quality as opposed to a 2D based ortho. This is also something Mohsen was referring to. The buildings don't have a lean. You can see the edges are very clean, perfectly rectified. The data next to the buildings is still in full detail, even when you switch from the shadow to the highlight. Or if you look at very, very bright rooftops or building tops, they still maintain the highest level of information, even in the white areas. Okay. So that's the Little Rock. And in the 3D, it's also critical because the oblique images will also have tall buildings that view things in full shadow. So you see here the ability to utilize maximum details in the shadow also means good quality of data in that part. So being able to extract all the details in every single pixel. Okay. Just a second. Yeah. And over here we can see in PhotoMesh the project similar to Denver, except this has 4 obliques in the nadir. And just wanted to go over real quick different editing tools or cleanup, let's say for water bodies. In this case, you could import a water poly if you have hydrography layers, or you could just digitize it in the software. And you can see the water polys then get applied to have very, very clean water around the bridges, under the bridges. And that's different options for also doing a little cleanup or editing on the mesh or the ortho. Okay, we'll jump into this one. Here we go. So the next project we'll look at, it was 4mm GSD. just over half a kilometer, square kilometer. This is a fixed wing drone, so already a single camera system as opposed to 6 cameras or 7 cameras. The collection is less intensive, but you can get very good GSD. In this case, better than half a centimeter, 4 millimeters. It doesn't require as many fusers, so this is something that could be done more on site or with a smaller production center. In this case, 20 fusers were used. The IQ conversion, 1.5 hours, and this is something more reasonable. Even on a single laptop, it would be over 2 days with 20 fusers, could get it done in 5.5 hours. This focus for this product was a 2D ortho. So we will look into the fixed wing. Here we go, the P5. And this was also imported with the IIQs directly using the IIQ configuration and then converted inside the Skyline software. So we can see over here the a little bit more erratic drone flight, not like nice straight lines from an aircraft at high altitude. Um, does have enough coverage to produce the 2D terrain-based ortho. And we can see in this case, it was only 71 reconstruction tiles, which is also why the process is more efficient, smaller data set, smaller area. We can see over here the quality, same in the shadows, and in areas with a lot of vegetation, you can see how critical it gets because you could have areas inside the shadows that are fully covered. You're still getting details switching between the illuminated and the shaded parts. Okay. And the resolution is very, very high. It's 4 millimeters. You get into individual wires inside pickup trucks. So it's getting very impressive. Okay. And we will jump into the last one, which is the P3. The P3 is more for 3D inspection, more hover drones that fly slower or in orbits. In this case, you see the flight was done in ascending orbits around the tower, and collected almost 2,000 images, a lot of images for an inspection projects, especially from a camera of this size, so 226 gigapixels, and also processed on 20 fusers like the previous project, so more of a drone type configuration. Um, Once again, IIQ, just over an hour. The aerial triangulation took 2 hours, and reconstruction on 20 fusers took 6 hours. And this is the full 3D reconstruction. So total process completed in 9.5 hours. You see 5 days on a single laptop, 9.5 hours on a multiple fuser architecture. Okay. We'll look at the PhotoMesh project first, just so that we could see the process for the 3D reconstruction, you know, from the IIQs. And the difference between what we saw up until now, which was more mapping, area mapping, this is more inspection. And with inspection, the focus instead of 2D area, that's why it's not really relevant what's the area. It's more of how much data you're capturing, vertical data. The tiles get divided vertically. So you can see as opposed to 2D tiles for an ortho or city type urban 3D model, for inspection purposes, the project gets divided into vertical dynamic tiles. And that's how it can divide it into multiple fusers, but still produce a single comprehensive mesh. Okay, so That's what the flight looks like, all the images. And when the mesh is complete, one of the things that could be done both in the Terra Explorer desktop and the Terra Explorer Fusion is the mesh could be brought in along with the original IIQ converted images from PhotoMesh. And essentially, any area on the mesh that needs further inspection or needs to be reviewed with the images could just be, say, if we want to review this screw over here, you can just zoom on it, click over here, and it'll load the relevant images for it and also allow measurement to happen on the image itself. Okay, so at that point, you could measure, let's say, the pole on the image, and it'll make the measurement on the 3D model as well. Okay. So, and this is the 300 micron 0.3 millimeter GSD. See the zoom level that you get to is incredible. You can see individual pebbles in the tower, measure individual screws, and really see any piece of detail that um, exists in the tower, including all of the ladder steps and numbers on the wires themselves, such as these. Whoop. Okay, and this is also available in the Fusion project. There we go. So this is what we're looking at with all the photos. Okay, I think we're at 10 minutes left, so I think we're at the QA portion. Um, Let me check. Okay,
Phew. Thank you so much, Itai.
excellent.
Probably I can now start sharing my screen. Perfect. Thank you so much, Itai. It was really great that you took us to the journey of submillimeter towards countrywide mapping with phase one and Skyline solutions. I have a question for you because there is no doubt here that you can use phase one images for measurements. It's always a matter of scale and how far you can be from the object. But sometimes you answer this question indirectly. How can you describe the productivity with phase one and Skyline solution, right? You talked about the fusion of your fusion solutions that you have, distributed processing, multiple users, you can deliver faster. And at phase one, we have also the IIQ image that you are integrating in the workflow. That means we can deliver the data also faster. How is it in aerial survey? You talk sometimes about you can save fuel, you can save batteries, you can, these type of costs are always coming to the account. How do you see that?
Yeah, it's a good point. On the aerial side, I think the main advantage is being able to start the processing as soon as possible. Even on the field, with aerial systems, there's a very lengthy post process of converting images, converting GPS data, and getting it to the point. It could be 2 days before you know if the flight is good or not. And this is something that even in the field, you could run a very rapid 2D ortho or just the AT process. You get the coverage, you get the connections, you get a sense of whether the flight is good or whether you need to do a completion flight the next day. One of the most expensive things with aerial mapping is mobilizing the aircraft. and you don't want to leave a site before you know a mission is done. So that's where working directly with IIQs lets you do a lot of things on site and not have to ship it back to a large production center and wait with large amounts of data. On the drone side, I think the critical thing is, the megapixels. Most non-professional cameras, drones, even if they're 20, 30, 40, when you're at 120 and a high quality lens, you just need to capture less images, and you could do it with less batteries and get better resolution on the same flight time. So for inspection purposes, it's critical. There's only so much inspection you could do with 5 millimeters, but there's a lot more inspection you could do at 1 or 2 millimeters, and that's the difference in the resolution.
Perfect. Thank you so much. I have always this question from some of our customers. They say, "Oh, phase one, specifically in drone industry, they ask phase one images are uh, large or too large." And my answer, it would be the same as yours. Yes, and with that large images, you can capture less images compared to having small footprints and always taking care of overlaps and having more images to cover that area. Perfect.
Correct.
Thank you so much. I liked the um, part of your presentation that you showcased the inspection part, right? It is not always uh, processing and producing 3D meshes, but it was really interesting that you showed how you can click on the 3D mesh and also see the original image. Is it also possible that if you have only aerial triangulation results and bringing that to the photo mesh without producing sub-millimeter resolution and just going to uh, oriented images and also showcasing the inspection?
Yeah, so we do have customers that use the AT results to bring it into other 3D viewers, and I know that there's a lot of new innovation in terms of using the 2D image in the 3D frustum for AI, like antenna detection, asset monitoring, and things of that nature. So as part of the PhotoMesh result, you could take the corrected orientation, camera model, position, everything from the cameras and bring it into any 3D. It could be with OBJs or 3D tiles or really any sort of mesh format, and then associate the AT results with the mesh. We can allow you to do Terra with Terra Explorer. Terra Explorer is an API, so you could essentially use the photo inspector to do the association of the 2D image with the 3D frustum. But yeah, at the end of the day, we export the AT, and you could utilize it in whatever third party software you want. I saw a question I can
Perfect.
address on
Yes,
mixing
please.
SLAM LiDAR. Do you want me to address that?
Yes, please. Go ahead.
Yeah, so PhotoMesh supports importing LAS, LAZ, or E57 files, point clouds. And if you have a point cloud that was collected either with the camera or at a separate collect, um, you saw PhotoMesh has a control point mechanism. You could pick control points from the SLAM LiDAR and then correlate the images with the LiDAR so that they're perfectly co-registered. And then you could utilize the LiDAR in the 3D reconstruction to have a more detailed mesh or just higher fidelity from the LiDAR scan. So you could do that with any combination of images and point clouds from any sensors.
Thank
Okay.
you so much. Maybe I can just share the results of the polls here, just which covers some of our questions or the questions from the audience here. Um, the majority of the audience, it was not that much, so around 60%, they were concerned about slow processing speed in their existing software that they are using. So it's very applicable that you talked about the speed, the how to scale up business in distribution processing and fusion of the users. And the next was ensuring the accuracy and QA in probably data delivery. I think it's very important that people use the right way in IX Flight Pro or IX Process or any software they have. And also there are a lot of tools in Skyline solution to do the QA. It would be, AT results towards the 3D reconstruction. And the last concern that they had, the integration of imagery inside their workflow and also integrating with other data like LiDAR. So it is somehow I would say in the same rate, the second concern. And the last point, which was the 30% of the audience, complexity of the software. So they need simpler software. And I can share the results of the first poll. So more than around 70% of the audience are doing digital twin, 3D digital twin, smart city, somehow in the range of 2 to 10 centimeter. And the second is surveying and construction from 5 millimeter to 2 centimeter. And the third is inspection and infrastructure, sub-millimeter to 5 millimeter. And the last is the 30% of the audience to the local and regional wide area mapping. So with that, I would like to thank you very much, Itai, for being with us.
My pleasure.
And, and thank you, Anika. Anika helped us from the marketing team in the background in managing the polls and the whole presentation. And thank you, everyone, where you are in the world, uh, being with us. And if you have any questions, just reach out to us. We will have also in the email that we will send regarding the recording, the instruction and also the workflow that Skyline has it on their website that you can see how you can manage your data with phase one cameras inside the Skyline workflow. Thank you so much.
Thank you,
Stay
everyone.
tuned. Bye for now.